My name is Shayon Lim, and today I'm going to talk about the fifth lab of the Physics 2212, which covers Faraday's law. The purpose of this lab is to observe and analyze the interaction between a falling magnet and an aluminum tube, which was used instead of copper wire, to derive the Faraday's law. The result turned out to be that the actual value for the time was 1.25 seconds. However, the model turned out to be 0.31 seconds, which is totally off. For the assumptions and initial conditions, negligible resistance is assumed, and for the system, magnet and cylinder or the foil would be the system, while the surrounding should be everything else. The initial condition is the magnitude and the tube given by the instruction in the file. There are mainly 4 or 5 physics law or principles that was used for the experiment. First is the Faraday's law, second is the Biot-Savart law, third is the Newton's second and third law, which would be used to explain the results, and fourth would be the Ohm's law that would be used in what if and why section. The model was pretty simple. It was just an aluminum foil, cylindrical aluminum foil, and a magnet falling through it, and there are mainly 3 forces acting on the magnet, considering that the other resistance are negligible. The values are given as below, and especially the value for the thickness of the foil there were some difficulties calculating the value, so it was taken for the minimum and for the average of the minimum and the maximum aluminum foils that are out in the market. For the questions, ferrous tube will interfere with aluminum foil, which would make it difficult to interpret the results, and if the bar magnet moves in the free space, it'll just draw faster. These are the glow script codes that were used for the experiment. All the values were put in, and then the velocity, dipole, r magnitude, r hat, and finally the value of B using the Biot-Savart law was calculated. And the code goes on and on until it reaches at the end to set the net force equal to gravitational force and equal to the sum of the gravitational force and the magnetic force. This was the result, which turned out to be 0.31 seconds for the bar magnet to be dropped. And since there aren't any points that seems for the slope to be equal 0, it means that there might be something off with the calculation or the values that were used. For errors and discrepancies, errors should have occurred during the time measurement process, and considering that there were only 5 measurements taken, this would not be enough for the derivation of the correct results. Still, the biggest error and discrepancy come from the mu value, which turned out to be too low. What if and why? What if the resistivity of the conductor were reduced as close as possible to 0? Then as the current increases following Ohm's law, the time that takes for the magnet to pass by the tube should have increased also. What if holes or slots were cut into the tube? How would this affect the ring currents in your model? Considering the decrease in number of rings, or the n value, this will result in an overall decrease of induced current, which leads to the shortening of the time for the magnet